Okay, in this lecture, I'm going to go over the solutions to Handout 21C. So in question number one, we have a spherical shell that is a conductor with a net charge of plus 3Q on it. And this shell has an inner radius of R1 and an outer radius of R2. And there's a charge negative Q in the center of the hollow portion, okay, in the center of the shell. So question number one, or part A, is what is the electric field at a radius of R that's less than R1? Okay, so I've just drawn, this is part A. This could be, for example, my Gaussian surface for part A, because I want to know what's the electric field at any point on this surface, because this is at a radius, so here's my radius, that's less than R1. All right, so that's question A. So I've redrawn the situation here. Here's my Gaussian surface. It encloses a charge minus Q. Now there are some charges outside, right? Because that shell has a net charge of plus 3Q. But remember that anything outside of my Gaussian surface does not contribute to the flux through the surface. All right, so now I'm ready to use Gauss's law. So remember, Gauss's law says that the electric flux through the surface, which is calculated using this surface integral here, is equal to the charge enclosed by the surface divided by epsilon naught. So there's a couple of arguments we're going to make from symmetry here. One is that the electric field must be the same everywhere on this surface. And the reason for that is because every point on this surface is the same distance from the charge. Okay, so all of these points are equally distant from the charge. Therefore, E, the electric field, at least its magnitude, is a constant on the surface, everywhere on the surface. That's going to simplify the integral later. The other argument we can make about the electric field, this time about its direction, is that it must be pointing away from, or I'm sorry, in this case, towards the negative charge. So if you like, you can think of this as we're using some prior knowledge about what the electric field lines due to a negative charge would look like, but prior knowledge isn't really required. We can make this argument out of symmetry. Because this is a spherically symmetric scenario, then the field lines have to be spherically symmetric, which means that they're going to be radial. Now let's figure out what E dot n looks like. So for that, we need to establish what does n hat look like. N hat is the normal to the surface. So at each of these points where I've got an electric field line coming in, the normal is going to be pointing outward. Right? So n hat is outward pointing, and electric field is inward pointing, everywhere. So everywhere they are anti-parallel. The angle between them is 180 degrees. So E dot n hat is going to be the magnitude of E times the magnitude of n hat, which is 1, times the cosine of theta, and theta is 180 degrees, so this is negative, equal to negative magnitude of E. So let's take this result for E dot n, put it into our integral up here, and I get that the integral, the left-hand side of Gauss's law is equal to the integral of negative E dA. And we established that E is constant on the surface. So since we're integrating over the surface, E is the same everywhere on the surface. So E is a constant in this integral. So I'm going to pull it out. I'll pull out the negative sign too. And the integral is reduced to something very simple, which is, remember, an integral is a sum. So this is the sum of all the little small areas, all the dAs that make up the surface, and we're doing that sum over the entire surface. So by the time we've added up all the tiny areas over the entire surface, we have added up the total surface area. So this ends up being surface area. of our Gaussian surface, which is, for a sphere, 4 pi r squared, where r is the radius of our surface. R was something um, that we made up, but it's less than r1 as required. Okay, so now the charge enclosed is negative q. So now we can put everything together. All right, so we found the left-hand side as negative magnitude of E, 4 pi r squared. And the right-hand side is charge enclosed, which is negative q, over epsilon naught. So the negative signs cancel here. I'll talk about why that is, why that makes sense here in just a minute. And then now I'm going to solve for E. One over 4 pi epsilon naught q over r squared. So this is, in fact, the electric field due to a point charge, as we've seen before. Now you may be wondering, why isn't it negative? Because I have a negative charge here, so the electric field should be negative. But because I used this version of the dot product where I substituted E dot n with magnitude E, magnitude n, and cosine theta, I have magnitude of E is what appears on the left-hand side here. So this is actually correct even for a negative charge, because if Q were negative, then the magnitude of E is still going to be positive. Okay, so here's our result. So this is just the electric field magnitude due to a point charge. All right, now I'm going to do part B. And part B is asking about how much charge is there on the interior of the shell, of this conducting shell, on the interior surface. And it gives us a hint when it tells us in the question that since this is a conductor, a conductor in equilibrium, then we already know the electric field must be zero everywhere in here. So if I draw my Gaussian surface so that it lies just in between these two radii, then first of all, I know the electric field everywhere on the surface must be zero because the conductor is in equilibrium. So that's one reason I choose this surface. And another is because it includes, inside of this surface, it encloses the inner edge of this shell, which is where I would like to know how much charge has accumulated. Okay, so this shell here is going to be for part B. Okay, once again, I redrew the situation where I've got the Gaussian surface here with a radius r that's greater than the r1. It's less than r2, but I didn't draw r2. In fact, I didn't draw anything that's outside of the Gaussian surface. And that's because it doesn't have any effect on the flux if it's outside the surface. And it helps clean the picture up a little bit. So if this is helpful to you, I would suggest trying it, which is draw the Gaussian surface, but leave out, don't draw everything that's outside the surface. Okay, so here's Gauss's law. I wrote the flux through the surface as phi e, which is just shorthand for that integral of E dot n dA. And we know that since E equals zero everywhere on the surface, and again, it equals zero because we are inside a conductor that's in equilibrium, and therefore the electric field everywhere inside the conductor and within the material itself is zero. And this dotted line is within that material, within the conductor material. So if E is zero, then the flux, the electric flux through the surface, if E is zero everywhere on the surface, must be zero. And that equals the charge enclosed over epsilon naught. And so clearly, if I multiply both sides by epsilon naught, the charge enclosed must be zero. But I have a negative Q right here in the center of the hollow part of the shell. And so, but the charge enclosed by this Gaussian surface needs to be zero. So that tells me right away that I've got a charge plus Q distributed around the interior surface of this shell. Okay, so plus Q is along the inside. And then C, so plus Q, and then C, the question is, therefore, how much charge must be on the outer edge of the surface? Because remember, with a conductor, the charges, the net charges all accumulate on the surface of the conductor. So I've got Q on the inner surface, but I've got a total of 3Q total. So that means the outer surface must have the other 2Q on it. Okay, and then back to my original drawing. Lastly, for part D, we're going to do this surface that is outside the entire shell. Okay, so this surface has a radius that's greater than R2, and this is going to be for part D. Okay, so I've redrawn the situation. I've got my Gaussian surface that encircles everything, and the question is, what's the electric field along this surface? So this is very similar to part A. I can make the same symmetry arguments that E is constant everywhere on the surface, and that it points well, it points radially. I don't know yet whether it points away or towards. We can figure that out in a minute. But E is constant and E is radial, meaning it points along a radial line, either away or towards the center. One reason we can make that approximation is, again, because of symmetry. We know that this charge 3Q is evenly distributed everywhere on the surface, inner and outer surface of this. So no point has any different perspective, if you like, than any other point. Okay, they all see the same thing in their immediate neighborhood because everything is evenly distributed in a symmetric fashion. So the flux through the surface works out just as it did in part A. It's going to be E, which is the magnitude of the electric field on this surface, times 4 pi r squared. And that's going to equal the charge enclosed over epsilon naught. So now the charge enclosed by this big surface here that I've drawn, this is 3Q minus Q, so total charge enclosed of 2Q over epsilon naught. And now I can solve for E. And E is 1 over 4 pi epsilon naught, 2Q over R squared. So this is what we would expect for a point charge with a charge of 2Q. This would be its electric field. So this shell and the charge inside and the charge on its surface, all together, when you're outside of the shell, it acts like a point charge. As far as the electric field is concerned, it looks like that of a point charge, which has a charge of 2Q. Now I mentioned the direction. So this has no direction information in it, right? Because I've taken a magnitude. All this gives me is the magnitude of the electric field. If I want to know the direction of the electric field, I can follow a similar line of reasoning, which is that since the net charge is positive, and this looks just like a electric field for a point charge, a positive point charge has electric field lines that point away, and so the electric field is going to be pointing outward, radially outward everywhere. Moving on to number 2, here I've got a coaxial cable. And a coaxial cable, that's like the kind you see that connects to a TV, where you have an inner wire, and then this outer shell also carries a current, and they carry currents in the opposite directions. TV connections have mostly been replaced by things like HDMI now, but if you have an old-fashioned antenna, it still connects to your TV using coaxial cable. I have an antenna for my TV. It is a high-def antenna, but it's still an antenna that uses a coaxial cable. So the first question is, if I1 is equal to I2, what is the magnetic field out here outside of the coaxial cable? So first of all, this is our Amperian loop right here. We gave it a radius r. And that radius r is bigger than radius r2, which is the radius of the outer shell of the coax cable. And the question is, what is b at any radius greater than r2? For example, this one. And here we're going to apply Ampere's law. And remember that Ampere's law tells us that the magnetic field strength along this loop is proportional to the amount of current that pierces through the loop. So imagine the soap bubble that fills this hoop here. How much current is piercing the soap bubble if I1 and I2 are equal but opposite? Well, if I have I1 going left to right and then I2 an equal amount going right to left, then I think it's pretty straightforward to conclude that the net current going through this soap bubble here is 0. And we'll talk. We have to be more precise here in a minute about which of these I1 and I2, which one's positive, which one's negative. But for now, since they're equal and opposite, we can conclude that they cancel, and so the net charge the net current that passes through this soap bubble is 0. So if the net current passing through the soap bubble is 0, then the right-hand side of Ampere's law is 0. Therefore, the left-hand side is 0. Therefore, B is 0 everywhere outside the coax cable. And this is the reason why coaxial cables are used. One reason that coaxial cables are used is because I1 and I2 are often the same, and so there's no magnetic field outside of the cable. All right, now part B is asking, what if I1 and I2 are not equal and opposite? What if I1 is greater than I2? Then the question is, what direction is the magnetic field? And to do this, anytime we define a direction for a magnetic field, if we're talking about the magnetic field around this loop here, we're either going to be talking about a clockwise or a counterclockwise magnetic field. Well, our answer, clockwise or counterclockwise, will depend on whether we're looking at it from the left or whether we're looking at it from the right. Because if we look at something from this side and it's going clockwise, when we look at it from this side, it's going counterclockwise. So this becomes, when you're talking clockwise and counterclockwise, your perspective becomes important. So the suggestion in the problem is to look at this thing from the left side. All right, so that's choosing our perspective. So this is the schematic for a human eyeball that's often used. So we've got our eye over here looking into the left side of this cable. Okay, so I'm going to redraw what it looks like from this perspective, from this eye being right there. Okay, so from the point of view of this eyeball that's looking in from the left, you can see that current I1 is going away from the eye, and current I2 is coming towards the eye. So that's why I drew it like this. I1 is going away. This is the coaxial cable. I2 is coming towards. Now I2 is actually distributed over this entire cylinder here, but I just drew it in one point, much like it was just drawn in one point right here at the top. So I drew it at the same place. And then R is our the radius of our Amperian loop that goes around the coaxial cable. By the way, it's called coaxial because we have got this inner wire and we've got this outer shell, and they both share an axis, meaning that they both are concentric. Okay, so that's why it's called a coaxial cable. Okay, now which of these currents is positive and which is negative? So if you haven't watched my Ampere's law video, please go back and watch it, where I talk about this in some more detail. But the convention is, first of all, we're going to follow this path in a counterclockwise direction. That's not necessarily the direction of the magnetic field, but that's the direction we're walking this path. So that's the direction of DL. And our sign convention is basically to make sure that the right-hand rule number 2 is obeyed. I'm going to follow this DL, the direction I'm walking around the path with my right hand, with my fingers. And my thumb is going to point in the direction of positive current. So if I'm walking the path counterclockwise, my thumb comes out of the page. So that means a positive current comes out of the page. So which of these is positive? I2. So I2 is positive. Because it's coming out of the page, it would agree with the right-hand rule for if my fingers follow DL. And I1 is negative because it's going away from us. All right, so we're almost ready to compute this path integral. We just need to know the direction of B. And B is either going to go clockwise or counterclockwise around this loop. If B goes counterclockwise, then theta is 0. And if B goes clockwise, then it's going to be anti-parallel. It's going to be opposite everywhere to DL. So it'll be 180 degrees or 0 degrees. Now this is a place where we can use some prior knowledge. Since I have I2 coming out, I1 going in, and okay, so this isn't prior knowledge so much as we're going to make an assumption, see if it works, and then follow the other one if it doesn't work. So if I2 is positive and the net current is also positive, then by the right-hand rule number 2, we're going to get B parallel to DL. If the net ends up being negative, we're going to get B anti-parallel to DL. Okay, so let's try the parallel case first and see what happens. And then we'll figure out the direction at the end. All right, so the integral of B dot DL is going to be magnitude of B times magnitude of DL times the cosine of 0, which is 1. And B everywhere on this loop has to be the same because it's every point on this loop is the same distance from I2 and I1 as any other point. So B is a constant around this loop. So I can pull it out. And then I have the integral of DL around the loop. So that's just the circumference of the loop. So that's the left-hand side of Ampere's law. The right-hand side involves I net. I net in this case is going to be I2 minus I1 because I2 is positive, I1 is negative. So when we add them together, when we add up all the currents, we'll get I2 minus I1. All right, now let's put this into Ampere's law. So the left-hand side is this, B times 2 pi r. And the right-hand side is mu naught times I net, which is I2 minus I1. And now let's solve this for B. Okay, so there's the magnitude of the magnetic field. And I should put absolute values on this as well because I've got an absolute value on the left. And if I1 were larger than I2, that would give me a negative number on the right. So I can't have an absolute value equal to a negative number. So I should put an absolute value on this as well. All right, so this gives me the magnitude of B. And then the other part of the question is, what's the direction? So it tells us that I1 is greater than I2. So going up here, if I1 is greater than I2, then the net current is going into the page. If the net current's going into the page, I use right-hand rule number 2, point my thumb in, and my fingers curl around clockwise. So since I1 is greater than I2, then B is clockwise when viewed from the left. That was the perspective that we chose at the start.